let's take a look at their official data taken from NASA's website, the Great American Eclipse Path. NASA also provides external link for more details. This is a picture that destroys globe model if you understand what it means. First, let's find out the eclipse duration that began at the far west and ended at the far east. We're not looking for eclipse beginning and ending in one location, as there are so many locations. What we're looking is the beginning and ending of the whole eclipse happened on that day. You just click the path and they give you complete information. See, the start of partial eclipse is 1555 UTC. Then the end of partial eclipse 2055 UTC. Now we have credible data that total eclipse duration is 5 hours. Secondly, how far is that eclipse length? Take a look at the longitude. It started at 171.2 degree west and ended at 27.4 degree west. The eclipse length longitude is 143.7 degrees. Do you realize how far is 143.7 degrees in a globe? Let's copy-paste some coordinates from the eclipse site to Google Maps to measure the approximate distance. It's around 40,000 kilometers. Now, apply it to the globe map. See, the eclipse distance, 143.7 degrees, is already 40% of the Earth's circumference. So, within 5 hours of eclipse, out of 24 hours a day, or around 20% of the day, somehow, miraculously, the shadow length covers 40% of the globe. Let's make a scale model now to understand that the eclipse length of 143.7 degrees is mathematically and geometrically impossible. We've made scale model of the eclipse using AutoCAD. In this video, I'm collaborating with many people from Flat Earth 101 community. You have seen the work of Najwa and Anggol Aji specially made for you. For this AutoCAD, I want to make it as precise as possible, so I collaborate with people from the community again, this time with Tejo. He is a successful architect who is very familiar with AutoCAD. And he's not alone. People in his office also help us to make this model. They are flat earthers too. These are the assumptions I took from mainstream science database. We made this model based on that official data at that particular date and that particular spot as referred by NASA. Let's start with the Earth. Of course we can make it pretty with 3D Earth, but that's not our objective now. It's not about beauty, it's about precision. The Earth radius and diameter are precise according to heliocentric data. These 5 lines represent the Earth's rotation for 5 hours, the eclipse duration. Each line represents 15 degrees. 5 lines equal to 75 degrees. The 0 point represents the first second of the eclipse. The Earth rotates anti-clockwise from west to east. So if you are standing over here at 0 point, in 5 hours you will be over there. Now let's go to the moon. It's 30 Earth diameters away. The Earth is a small circle over here and the moon is over there. Let's zoom in. This is the moon at 0 point when the first second of partial eclipse started. These 5 moons represent its movements every hour, 1, 2, 3, 4, 5 hours. This is the moon's radius and diameter according to standard heliocentric. This is the moon's traveling distance every hour. Within 5 hours, it travels 18,415 kilometers. That's the linear speed. But the orbit is so big, 29.5 days, and 5 hours means almost nothing. So if you draw a line from the moon's axis to the Earth's axis, this 18,415 kilometers is only 2.55 degrees angular speed on Earth. It's hard to see at this true scale. Let's split it into 2 screens, the moon on your left side, the Earth on your right side. This is the 0 point when the first partial eclipse happened. The line goes to 0 point on Earth. In 5 hours, the moon will be over there. If you're standing on Earth over here, 5 hours later, you will rotate from west to east and you'll be over here. You will see the moon is setting to the west due to Earth's rotation. Exactly like you've seen at mooncalc, you add time, the moon goes to the west. And the elevation angle is subtracted from 90 degree to around 75 degree in 1 hour. For 5 hours, it would be around 18 degree near the horizon, almost setting. This is the proof that it's the angular speed that applies. What about the linear speed? After 5 hours, the moon's position is over here. We draw straight linear lines from the moon. Where do the lines fall on Earth? Man, it's far outside the Earth. Theoretically, linear speed is wrong. After 5 hours, you would see the moon is setting to the west. In reality, you don't see the moon is over here like it's setting to your east. The moon is over there, near the horizon, setting in the west. The funny thing is, even though the moon is over here setting in the east, the shadow will fall outside the earth. If you use angular speed, eclipse shadow moves from east to west, the opposite of reality. If you're using linear speed, the moon sets in the east and the shadow falls outside the earth after a few hours. Any which way, they're wrong. It really doesn't work on the globe model. What about the shadow speed? We've been through this. Their own science says the eclipse shadow speed is the same as the moon speed itself. Look once again at their eclipse shadow speed. The shadow is never faster than the moon speed.
The shadow knows.
Poor globe model. Let's be generous to them. Give the globe model a generous discount. Let's start not from 90-degree elevation, but instead from 0 degree like you have solar eclipse at 6 a.m. in the morning. You can't even see the sun at horizon level. Then you have 5 hours eclipse. And still, if using linear speed, the shadow goes outside the earth. Do you know why it fails? Because you can't get 5 hours eclipse on the globe model. The moon would travel 18,415 kilometers, while the Earth's diameter is only 12,742 kilometers. That would make the moon half Earth outside the Earth. This is real fantasy, folks. Congratulations. Based on their official data, you just found a fatal error on the globe model.